The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today we continue our theme of integer data structures, and today we're going to look at priority queues instead of the predecessor problem, so something a little different. Insert, delete, and find min. It turns out priority queues are equivalent to sorting in the sense that if you have, if you have an f of n, normally say f of n, but here we're going to depend on both n and the word size. Priority queue. Well, then, of course, you get a sorting algorithm. Just insert everything into the priority queue, and then find min, delete, and so on. So that's the trivial direction of the equivalence. But it turns out both of these are true. If you have a sorting algorithm with n times f time, then you can convert it into a priority queue that in the worst case, every operation takes only f of n comma w. So that's the equivalence as a result of Thorup from a few years ago, 2007. Kind of a cool breakthrough. There were earlier versions that weren't quite as efficient. But this gives you perfect efficiency, turning any sorting algorithm to priority queue. Rough sketch of the data structure is you have a bunch of sorting algorithms which you run now and then to get on little parts of the input in order to build an overall priority queue. But it's very complicated. There was an entire class project on assimilating it and understanding it. It's a bit beyond what we can cover in the class. So I'm going to take this as given and tell you instead about sorting algorithms, because there's a major open problem here, which is can you sort n integers, n w-bit integers and a word size w in linear time? We still don't know. But we have a bunch of results. In particular, we're going to talk about a couple interesting cases where we can get linear time sorting. If you've seen radix sort, you know another interesting case where linear time sorting is possible. Let's see, it's an interesting open problem here. Can you get constant time decrease key? And ideally also insertion. But decrease key would be handy because this would be useful for in this reduction. If you have a sorting algorithm like to get a priority queue with constant time decrease key, that would have applications to Dijkstra's algorithm. Of course, if you can sort in linear time, then everything can be done in constant time. So this is not the most interesting open problem, but it would be a step in that direction. Cool. So let me tell you some bounds about sorting. So we have n w-bit integers, and you take any of these bounds, divide by n, you get the priority queue bound, the best that we know. So of course, there's comparison sorting, which takes n log n. Okay, so that's an upper bound. We're trying to beat that. Try to get rid of the log. There's counting sort from undergraduate algorithms. That takes n plus u time because you need to build a table of size u. You've got to zero out all the initial counts. So that requires order u time. This is interesting, really, when the word size equals log n. So that's a case of potential interest, because then 2 to the w is just n, so this is linear time. But even if w is 2 times log n or 1.1 times log n, then this is bigger than n log n, so not very good. But we have radix sort, is a bit better, and this is n times w divided by log n. If you do it right, so you have some word size w, you're using counting sort for each digit in the radix, so you can afford that the word size of doing counting sort to be exactly log n, which means you have your overall word you're dividing into chunks of size log n. Each of them you can do in linear time. So the number of chunks you have to do is w divided by log n. And this is linear if w equals order log n. Right? But only then. So it spies you a little bit, but still not great. Okay, there's some other sorting algorithms we've implicitly seen because we've seen Van M. de Bois. I mean, any predecessor data structure gives you a priority queue data structure. Priority queues, I didn't say, or I didn't write it, but I mentioned insert, delete, find min. Find min is a weaker operation than predecessor or successor. So we can take Van M. de Bois predecessor data structure and convert it into a sorting algorithm, and we get order n times log w. Now, this is a little bit tricky to compare. Of course, log w sounds better than w, but there's this divided by log n, which makes it a little hard to compare. It turns out there's another version, or you could take this sorting algorithm and achieve a bound of n log w over log n. Okay, so this is a slight improvement in here. It's similar to your problem set this week. This specific problem was a problem set in 2005 of this class. So you can check it out if you want to see how to do this slight improvement. But now this is clearly better than this, because here we have w over log n. Here I've got a log in front. So this is a win over radix sort. So Van M. de Bois, here's another way in which it's interesting. It gives us a strict improvement over radix sort. And in particular, do I care? Well, actually, both of these are order n log log n if w is not too big. Poly log n. So this doesn't actually matter, but it's clearly better than this one. Again, if w is order log n, you get this to be linear. But in particular, it says overall you get n log log n up to w being polylog. Okay, why do we care? Because there's this other nice algorithm, signature sort, which covers all large word sizes. And this is an algorithm we will cover today. It only works when w is large, and large means log to the 2 plus epsilon n. This is no matter what epsilon is. In reality, it's probably log squared n times log log n squared, but be a little sloppy and just say, oh, a little bit bigger than log squared. And then it runs in linear time. Okay, so if you were graphing this in your mind, you've got time, and there's a nice bound here which is order n, and we have other, everything's above n log n. Maybe here we have, this is hard to draw, n log log n. Okay, this is asymptotic space, which doesn't really exist, but you know what I mean. And then this is the word size versus log n. Well, this is hard to do. This is a really weird picture. Never drawn this before. So we initially, radix sort. Okay, log n. We could do that. We could get linear time. Okay, or order log n. Great. What this is saying is once you get out to log to the 2 plus epsilon n, you can also do linear. And from here over, we have linear time. And here over, we have linear time. So the question is, what about this middle range between log n and log to the 2 plus epsilon? Well, one thing we could do is use Van M. de Bois sort, get an n log log n bound. And so that's one way to fill in this range in the middle. And that means overall, you can always sort n integers in n log log n time. If w is big, you use signature sort. If w is small, you use Van M. de Bois sort. So this implies n log log n for all w. So that's something. It's not the best known. Let's see. First result in this direction is by Han in 2001, and it achieved this bound deterministic and in the AC0 RAM, so without using multiplication, which I guess Van Emden-Boas doesn't either, unless I'm missing something. So, but it got rid of the randomization, which is necessary to get linear space in Van Emden-Boas. And the current best result on sorting is by Han and Thorup in 2002, so a while ago. They achieved n square root log W over log n, which is similar to this bound, just has an extra square root here. So it's a little bit better than Van Emden-Boas sort. It uses some clever tricks. It is randomized. So still the best deterministic bound is n log log n. And let's see. We can plug that in for this range here, and it will imply that you get n square root log log n for all w. Because in particular, if w is order, if w is poly log n, then this is just log log n. So you get this bound. Of course, for all w, because large w are already covered. So this sorting algorithm is a little bit messy and possibly not the right answer. I would conjecture you can sort n integers in linear time for all w. But that is a big open problem. This is the current state of the art. This open question is really about for small w, when w is poly log n, or actually when it's between log and poly log. So to give you a piece of the complete picture, I want to tell you about signature sort. So I think you have to use different techniques when w is small versus large. We know that from fusion trees and Van Emden-Boas. So I'll tell you about the slightly large case when w is at least log to 2 plus epsilon, how to get linear time. And this is fun. It uses bit tricks. It uses a lot of cool ideas. It uses hashing, lots of things. It also uses another sorting algorithm called packed sort. This is not, doesn't fit in the regular table because it's for a situation when more than one input number fits in a word. So we're going to let b denote the number of bits in the inputs. So we have b-bit integers. Then when w is at least b times log n log log n, so you can fit log n log log n integers in a single word, then you can sort them in linear time. So it's like your machine is just a little bit bigger than what you'd need to represent the integers. Then all sorting can be done in linear time. And as you might imagine, this log to the 2 plus epsilon buys you a little bit of room with some tricks, namely sorting, namely hashing. All right, but that's where we're going. And we'll use yet another sorting algorithm by tonic sort, which you may have seen. It's a sorting network. It's in CLRS up to 2nd edition, but it got removed from 3rd edition. I guess they thought people didn't use sorting networks, but we use sorting networks here. Because it gives us parallel sorting, and the word rem is all about using the parallelism in your word. So we'll get to those. I'm going to start at the top level, which is signature sort. And we're going to leave things to be done, and then pack sorting will be one of them. And bitonic sorting will be used in pack sorting. So it's a chain like this. Cool. So I'm going to assume my signature sort that w is at least log to the 2 plus epsilon n times log log n. Okay, this is really just a change in what epsilon means. You make it a little bit, if you're given some particular epsilon, make it a little smaller, then you can afford to add that log log n factor. This is just for convenience. Now, here's the idea. This is a pretty cool idea, I have to say. It's by Anderson and others in 1998. Okay, our word size is big, which is both good and bad. It means the numbers we have to sort are big. They have a lot of bits in them, way more than log n bits. But also, we have this powerful machine that can handle words of very large size and do things in constant time on them. So what I'm going to do, I'd like to make some slop. I want my words to be bigger than my items. So first few steps are about doing that. The first idea is, well, you've got this giant word, log to 2 plus epsilon. So let's split it into chunks. And the number of chunks is log to the epsilon. So that means each chunk is, well, it could be even bigger. So it's at least log squared n, but it could be bigger than that. Because w is at least log to 2 plus epsilon. So we don't know. These things are of size w divided by log to the epsilon n, which is at least log squared. OK. Here's the crazy idea. So we're thinking of our number being divided into these chunks. It's being represented in some base, 2 to the w divided by log to the epsilon n. A bit of a mouthful. But think about these digits, right? I claim if you look at a digit, most values don't appear. Okay, because how many values are there for a digit? Well, it's at least 2 to the log squared n. That's a big number. That's way bigger than polynomial in n. But how many different digits are there? Well, there's n numbers. Each of them has log to the epsilon n digits in it appearing. And so there's roughly a linear number of digit values total. But the number of possible digit values is 2 to the log squared n, which is huge, super polynomial. So most digit values don't appear in our numbers. So what we're going to do is hash the digit values to reduce their space. Because they're currently living in a universe of 2 to the log squared n, but there's only n times log to the epsilon n of them. So we should be able to reduce to a much smaller universe. Using hashing, maybe, perfect hashing. Even. I mean, we don't have to be too intelligent here to tell you what we get. What I'd like is to reduce to a polynomial universe. And another way to say that is that the hash values are order log n bits. So this lets us go to n to the 10 or whatever, which is plenty of room, right? We take any universal hash function, then with, as soon as you get to roughly n squared size, I mean the square of the number of things, by a birthday paradox, constant probability, none of them will hit each other. That was the second level of perfect hashing. We don't need 2 levels here. Just say, OK, use order log n bits. You can set this to 100, whatever. Then with high probability, you will not get collisions. So none of the chunks will hit each other. So I'm omitting a step here, which is how to, OK, I'm omitting a couple things here. One of them is, all right, I want to do this in linear time. Everything has to be in linear time. So one fun part is I have to compute the hash value of all of these digits in a single word in constant time. Okay, so brief aside, how would I compute a universal hash function, all of these digits individually in constant time? Well, my personal favorite universal hashing scheme is the multiplication method. You just need to multiply by a single value m, and then take it modulo something. So if I do multiplication, I mean, if you think of there being something here, something here, something here, something here, something here, m does multiply each of these individually. Well, that's a rough sketch. I want to hash each of these guys, multiply them by the multiplication method. This would work fine, except you get overflows, which is a bit messy. So in fact, I'm going to have to do it for the odd guys first, multiply them out, mask out the bits I care about, then do it for the even guys separately. So it's a bit messy, but hand-wavy proof. You can compute the hash function of each of these guys individually, but in constant time. So that lets me do this. You have to then check for collisions, which is kind of annoying. Let's not worry about that. Set this really high, very high probability there will be no collisions. Cool. So at this point, we have mucked up all the digits. The annoying thing about this hashing is we do not preserve order. It's a little weird for a sorting algorithm to not preserve order. Because the whole point is to put things in order. But it's going to be useful nonetheless. Right? So each digit has been mangled. Each digit is out of order. But of course, the sequence of digits has been preserved in some sense. All right, so what? Well, at this point, we can use pack sorting to sort what remains. In general, pack sorting can sort n b-bit integers, provided b is small, so w is at least b log n log n. That's the theorem of pack sorting. We're going to delay the coverage of this result till later. And I claim that applies here because, let's see, each chunk is now order log n bits, and there's log to the epsilon n bits. So b is theta log to the 1 plus epsilon n, and w is at least log to 2 plus epsilon times log n. Okay, so the ratio between these is as needed. It's at least log n times log n. Okay, so that's why this is good. These things were huge before. We've compressed them a lot. They were at least log squared. Now they're only log. And so now we can apply pack sorting. You can fit all these guys you can fit log times log items into one word, and that's going to make sorting easy somehow. That's to be done. But now the question is, what would you do if suppose we had pack sorting, how does this help you? Because this does not sort the original integers. It sorts these integers that have all of their digits permuted in some random way. We have no idea how the hash function reorders things. So we're not done with signature sort. It's called signature sort, of course, because of the hashing. You're taking signatures of each of these digits. Another word for hashes. All right, next step is to build a compressed trie. This is a term we haven't used yet. So I'm going to call these things that we sorted signatures. And how many people know what a compressed trie is? Okay, no one. Wow, just a few. So you haven't seen suffix trees yet. We're going to cover where compressed tries come from in a couple of lectures, but we get to see them a little early because they're cool and needed for this algorithm. So first notion is the notion of a trie. The word trie comes from retrieval, from old days when information retrieval was what's now called, I don't know, web searching or whatever. But now it's pronounced trie. It's just another word for tree, but where the children of a tree come from a fixed universe. So this is we've been working with tries all the time in pretty much every lecture for the last N lectures, last W lectures, I don't know, a lot of them. We said, oh, okay, well, let's just consider the space of all possible keys. You know, I've drawn this picture a zillion times. Even when we weren't doing Van de Boas, which actually stores all of these things, when we're thinking about fusion trees, like, oh yeah, so we're storing this value, and we're storing this value, and maybe this value, and we understand, you know, this corresponds to a 0-bit, these are 0 and 1 bits, this is a 1, 0, 1, whatever. So we understand how to convert a bit string into this picture. This is what we call a binary trie. I want to do the same thing over here, except it's not a binary trie. Now each digit is giant, so we're going to have some huge branching factor. So it's going to be more like a B tree. The first node has a whole bunch of children. I'm not going to even, it's 2 to the W divided by log to the epsilon n. That's the branching factor. Okay, it's big. That's the number of possible values in the first digit. Okay, so, then maybe this child has some node there, and maybe, this one. Actually, sorry, I didn't want to draw it that way. I have a specific try in mind, or part of it. Okay, try is going to look something like this. It's just it's harder to draw, but it's the larger than binary equivalent of this picture. This would be a try. So let's think about a particular situation, which is, suppose we just have 2 items in this structure. Okay, then it's a little easier to draw. So let's suppose there's some item over here, x1. There's some item over here, x2. Now, generic picture is they share some common prefix. This is the common prefix. It's just to understand some particular picture here. Then they diverge, then they have their own digit values. In some sense, this is the digit value we care about because it distinguishes them. So there's this idea of a compressed trie, which cleans up this picture a little bit. The idea with the compressed trie is very simple. You draw this trie. So, here, imagine I'm erasing all the things that do not appear. Okay, maybe all this is gone. So I'm just keeping this part of the structure. Let's do it for the binary case first. The idea in a compressed trie is very simple. I'm going to contract every non-branching node into its parent. So what that means, so here I'm storing 3 values, 0, 0, 1, 1, 0, 1, 0, 0, and 0, 1, 1, 1. So some nodes are non-branching. That's this node, and this node. And the point is, well, why store those nodes? There was nothing being distinguished at that node, so contract it. So the new picture, if I redrew this, would be 0, 0, 1. Also this is non-branching. Okay, so in fact, I'm going to contract this into its parent, or this into its parent, this into its parent. So this whole path, this non-branching path, will be left with a single edge, which I will label 0, 1, 1. But it's a single edge in the structure. And over here we have an edge 1, and now we have 0, 0 here, and 1, 1 here. Okay, that is the compressed trie representation of these 3 values. The nice thing about this structure is every node is branching except the leaves, which means the number of nodes here is linear in the number of leaves. It's like twice the number of leaves minus 1, roughly. I guess the root might not be branching, but it has no parent to contract into. Whatever. One more nodes, most 2n nodes. That's the binary case. Now over here, what we do is, the corresponding contracted trie picture of this thing will be, let's see, it's the second edge. I'm going to put just a label of 2 on this edge to say, well, I'm skipping this node. This guy is non-branching, so I want to get rid of it and contract it into the parent. So now this corresponds to 2 edges here. There are 2 digits, which I could write the digits if I knew what they were. But particularly, I want to keep track of the fact that there are exactly 2 of them. And then there's a branching node. That one stays. But then actually, we'll go straight to the leaves here. This will be x1 and x2. And this will have a lot of digits. Okay, so some large number written here. So that's the idea with a compressed trie. Now, the nice thing about a compressed trie is they have linear size. Number of edges and vertices is linear in the number of leaves, which is the number of values we have here. Another nice thing about compressed tries is they preserve order. So if you look at the order of the leaves down here, it's the same as the order of the leaves over here. Right? We're not really changing order. We're just making things a little shorter to write down. Same thing over here. I mean, x1 appears to the left of x2. So say the order of the leaves is preserved. The other cool thing about compressed tries is you can compute them in linear time. But let me tell you why we're drawing this picture. Right? We've messed up all these chunks, all of these digits. What does that correspond to in this picture? We've permuted all of the children in this node. We've permuted all the children in this node, permuted all the children in this node. But otherwise, the structure of the tree is correct. What we wanted to do was compute, if we could compute the compressed trie representation of the original values, just having broken the integers into these pieces, then if we had that trie, we could just do an in-order traversal, find the order of the leaves, then we'd have the sorted order of the integers. Instead, what we've computed is not the correct, we didn't compute the correct compressed trie, but we computed a different compressed trie where every node has its children permuted. So all we need to do is put the children within each node in the correct order. Then we would have the correct compressed trie. Okay, that's why we're doing this. But first, how do we compute a compressed trie in linear time? This is a simple amortization argument. Okay, remember what we're given. At this point, we are given the leaves in sorted order, right? We've just sorted our things. So all I'm trying to do is compute the trie of the stuff above the things. Okay, we're given the leaves of the trie in the correct order. I just need to build the compressed trie. The reason I'm building a compressed trie is so I can do it in linear time. Constructing the uncompressed trie would take too long. Okay, so how do we do this? So we have our items xn in order. I want to just insert it into the compressed trie. So I start with an empty compressed trie. First thing I do is add x1, so it's just a single leaf. Then I add x2 to the trie, x3 to the trie. In general, I'll have computed, I'm going to draw a picture, how to draw a partial trie, something like this. I've computed the left part of the trie already. All these xi's have been done. And now I need to add on the next, say, xi over here somewhere. So think of how that would look in the trie. It has to come off of the right side. I guess what do you call this? The right spine of the tree. Some rightmost node over here. We want xi to be a new to the right child. So maybe, so one possible picture is there was some node which had some other children. Maybe this one had xi minus 1. And maybe xi belongs over here. Maybe this leads to xi in the uncompressed trie. This could be a potential picture. In the compressed trie, this node either exists or got contracted. If it exists, maybe there was a previous, like xi minus 2 belongs over here. So we already had this node because it distinguished these two xj's. To add the xi is really easy. I just add a node here, which points to a leaf of xi. So that could be one situation. The other situation is only slightly more complicated. So the other possibility is this node didn't exist in the compressed trie, which means we jumped over it in the compressed trie. Some number bigger than 1 here. Maybe you skipped 3 nodes. Who knows? So now this node matters. It didn't matter before. Before it was non-branching, but now we add xi. It's branching. All we do is update, add this new guy, add the new pointer to xi. Okay, so constant work. Great. Constant work per xi inserted, linear time overall. Not really. I've cheated a little bit here, which is, how do we know where to do this operation? So the changes we make is constant. That's fine. But how did I find that this was the edge where I need to put xi in? You can't do it in constant time, but we can do it in constant amortized time. So what we're going to do is start at the rightmost. Ooh, that is not very red. It's not a red chalk. Okay, here's some red chalk. We start at this leaf, the rightmost leaf, which you go going rightmost as possible. We're going to walk up the tree until we find the right point. I'm going to spend linear time in this path walk. Okay, how could this possibly be okay? I think you believe that I can do it in linear time, right? Each point I see, what is my common prefix with, actually an easy way is right up front. This thing right here is xi minus 1. These are single integers, so I can just compute their XOR, find the most significant 1 bit, which we did with the fusion tree lecture, and boom, I know where they differ in bit position. By some rounding, I can figure out which chunk they differ in, just by dividing, taking the ceiling. So I know the correct depth, and then these numbers tell me how much depth I'm losing. As I walk up, at some point I'll discover, oops, I just jumped over the depth I care about where they differ. And so at that point I know to do the operation. So if there are k edges here on the compressed trie, I can do this in order k time, k plus 1, let's say. Why is that okay? Because my potential function, amortization, is going to be the length of the right, let's call it the rightmost path. Okay, and before, my rightmost path was this thing. Afterwards, my rightmost path is going to be this thing. So it got roughly k shorter, k minus 1 shorter. Okay, so I charge this k plus 1 cost to a potential decrease of k minus 1. And so the amortized cost is only constant. Okay, easy amortization. Another way to see this is, overall, we're basically doing an in-order traversal of the tree. So whenever we walk up, we'll never visit these nodes again. And then we go down at a different place. Okay, yeah, this guy we're going to walk up again because in in-order traversal, we would have gone left and then come back to it and then gone down. So overall, we're doing an in-order traversal of the compressed trie. So it's linear time total. Okay. Still not done, though. What we have so far, what have we done? We've taken our numbers, we split them into digits. We randomly permuted the digits by a hash function. That magically let us sort them in linear time. Now we've built a compressed trie of that representation. The last thing to do is to fix the order of the children from each node. The tree is correct except for the order of the children in each node. So we've kind of sorted a little bit, but haven't fully sorted. So that's the last step. And we're going to do that with recursion. We're only going to recurse a constant number of times. Recursively sort. Okay, I'm going to walk through this compressed trie that we've built. And I guess it looks more like this. And for each edge, I'm going to write down this key. First thing I'm going to write down is the ID of the node. Let's say the ID is the in-order traversal index of the node. Okay, so boom. As we traverse the tree, we can just increment this counter. Then we also want what I'm going to put in here is the actual chunk value. that that's at the top of the node. So something like this, or I guess this one consists of two chunk values. So let's call them C1, two chunk values C1 and C2. It's the first chunk value and the second chunk value, the first digit and the second digit. Just write down the first one. That's really the only one we care about. The second one wasn't branching, so it's no big deal. Okay, so there's some chunk value. Now, I don't want to write down the signature chunk value. I don't want to write down the hash value. I want the actual chunk, original chunk, not the hash. That's why I write actual over here. And then also I'm going to write down the index of the edge. So this is the second edge, for example. Okay. Now this is in some sense the wrong index, and what I want to compute is where it's supposed to be. The edges have been permuted. So if I sort this thing, I claim that I'll find all the desired permutations. Okay. Why? Because if I sort by this three-valued, this triple, first thing I sort by is by node ID, then I'm sorting by actual chunk value, then edge index. I don't care that I'm sorting by it. That's just coming along for the ride. So what this tells me is for each node, it gives me the sorted value of the actual chunks, not the hash chunks. And then it tells me the order they used to be in. So this is a way to figure out the correct you want to figure out the sorted permutation of these things. This gives you the old index. And so once you sorted them, you know the new correct order is in order by chunk. And so this gives you, I guess, the inverse of the permutation over here of where each edge should be. So once I've done this, the last step is for each node, permute the edges as given by this inverse permutation. Question?
Can you explain again that you were basically sorting 3 times?
No, I'm sorting these single key values. The key value, the most significant part of the key is this. The next most significant part of the key is this, and the least significant part of the key is this. So imagine concatenating these things together into a single key value. Yeah, good question. Well, I'll talk about in a moment how big this key is. But if I sort by the concatenation of those keys, then what happens is I'm sorting by this and then sorting by this. But really, I'm doing one sort operation. This is one recursion. Other questions? Okay. Do you see why this gives us what we need? Right? For every node, we want to sort all those chunks. And so this information is just so we can keep track of the permutation when we're just sorting by value and not keeping the permutation. This lets us keep track of it. But our real goal is to sort all the chunk values. And we add in the node ID so that we just learn for every node what we're supposed to do instead of globally what we need to do. Maybe you don't have to do this, but it's easier to keep the node ID in there. OK, how many bits are in this key? So our whole point was to make chunks small so that the keys were small. But I claim this will be a little bit smaller than what we started with. So the node ID, well, there's only n nodes, so this is log n bits. Chunk value is, I guess, w divided by log to the epsilon n bits, right? Because there are log to the epsilon n chunks, so it's w divided by log to the epsilon bits. The edge index, how many different things were there? Whatever. Is it also w divided by log to the epsilon? I guess so. Depends how you count. Let me think for a second how these edge indices should be stored. I think I'd like to store the edge indices. I don't want to store the absent down pointers. Okay. The way that I built this tree, this compressed trie, I was always adding things to the right. So it's like, OK, I'm storing here. Here's the first child. Here's the next child. Here's the next child. Here's the next child. I just keep appending on. It's like an array that you can grow to the right, which you should know how to do in constant time. Even a linked list is probably fine. I don't want to store, if there are a bunch of values here that are just null pointers, I don't want to store those items in the array. Okay, so in fact, the maximum number of children of a node is n. I mean, at the worst case, you have branching everywhere. So this is only log n bits. to store the index in that array. So it's an extra level of compression. I guess I didn't mention. Don't store null pointers. Just skip them. And that's easy to do because always just appending. And in the end, what do I need to do here? Step 7 is in-order traversal of the compressed trie. And I output all the leaves I get in order. And the point is, we computed the compressed trie, which has the rough, correct topological structure. Then we fixed the order within each node. Now we have the correctly sorted compressed trie. And so you just do an in-order traversal, output the leaves you get in order. Boom, we've sorted all the items. Okay, a little crazy. So if all we need to do in the end is in-order traversal, then it's fine. We don't need to store the null pointers. So we don't need to be able to search in this trie. So this is enough. Clear? OK, the remaining question is how expensive is this recursion? So I computed the number of bits is basically w divided by log to the epsilon n plus order log n. The order log n won't hurt us. Now we started with integers of size w. Total size here was w. Now we have integers that their size is w divided by log to the epsilon n. So we've made progress. Cool. How much progress? Over here, maybe. So after, let's say, 1 over epsilon plus 1 recursions, we will have reached B will have decreased, excuse me, to order log n, I guess like 1 over epsilon log n plus w over log to the 1 plus epsilon n. OK. Right? If we take w and every time we divide by log to the epsilon n, then after 1 over epsilon times, we have divided by log n. Get rid of the epsilon. Do it one more time. We get w divided by log to the 1 plus epsilon n. Okay? And at this point, we're in good shape. Okay, if we get the size of our integers to be only w divided by log to the 1 plus epsilon n, then we can use pack sorting. Because pack sorting, conveniently, it's a black box at the moment, says, well, as long as w divided by b is a little bigger than log n, so here we've made it quite a bit bigger than log n, I mean log to the 1 plus epsilon n, bigger, then we can use pack sorting. So reach base case, and then use packed sorting. OK, the only thing is there's this log n. Now, epsilon is a constant here. So 1 over epsilon is constant. So this is just order log n. Order log n doesn't hurt you. I mean, if this happened to dominate this, then you're saying your values are order log n bits long, and so you use radix sort. Okay, so that's not going to dominate. In fact, you can prove in this case it's not going to dominate. W is at least log to the 2 plus epsilon. So you take w divided by log to 1 plus epsilon, that's still at least log n. Okay, so this will always dominate. Okay, so we did all this work, and all we did was reduce our word size by a log to the epsilon factor. But that's enough, because after we do that 1 over epsilon plus 1 times, we're small enough, the words are small enough, or the items we're sorting are small enough that we can use pack sorting. And boom, we're done. Okay, that is the beauty of signature sort. Any questions about that? Definitely not easy. But It works. The crazy idea is, well, decompose into these digits. I mean, we decompose into log to the epsilon digits because that would be enough. If we could get things down to a single digit, life would be easy. Which I guess is kind of like Venom de Boas, right? I mean, or it's like our lower bounds from last time. I don't know. Only one. If we could make it so only one digit mattered, then we could afford to do it because each digit is quite a bit smaller. I mean, it's smaller by a factor of log to the epsilon n. So we did that splitting, and then there was this observation that, well, most digit values aren't used. So if we hash, then things got a lot smaller. Then we can afford to pack sort, except that hash didn't preserve the order. How didn't it preserve the order? Well, when you look at the compressed trie, you see how it got messed up. Each node got messed up individually, but overall the structure of the trie was correct. So we did all this work to get the structure of the trie, then we had to fix the node order. But that's really just sorting a single digit. And yeah, we have to do it for all nodes, but you add them up. It's still only n items that we need to sort. So I wrote that b went down. N stays the same. The number of things we have to sort stays the same, which is fine. We're not trying to reduce n. We're just trying to reduce the size of our items to be a little bit smaller than w, so then we can use pack sorting. OK, I think I've gone over this algorithm enough times. The next step is pack sorting. Now that if we have integers that are much smaller than our word, how do we sort in linear time? And this is going to be essentially a fancy merge sort. Done in the same paper. Before we said omega, I'm going to essentially make omega a little bit bigger than 2. So I want to assume that w is at least twice b plus 1 log n log log n. That's just to make this convenient, but of course it doesn't really matter what the constants are. This will make everything fit in one word, though, instead of a constant number of words. OK, step 0 of this algorithm is the packing part. We can fit more than one element into each word, so put them in. Okay. Now we have linear time overall. This is easy to do. Just you have some word already. Take those items, shift them left or in the next item. Shift them left or in the next item. Shift them left or in the next item. Okay. Linear time. So in the end, what it's going to look like. Oh, I also want to leave a 0 bit in between each of them. So we're going to have b, this is going to be x1 here, x2, xn. Each of these is b bits long, and then we have one more bit. And in fact, the way we set things up, this is only half the word. So there's another half over here, which is going to be all 0 for now. So we have one word contains, or sorry, this is not n items. This is going to be log n log log n. Can't fit them all in one word. That would make life really easy. But you can fit log n items in the first word, then the next word is the next log n items, and so on. Okay, linear time to do that. Next step. This is an algorithm. It's not really a step, I should say. These are things that we're able to do, and we're going to combine them in different ways. So the next thing to observe, this is a sort of bottom-up perspective. So first thing we can do is pack things into a word. Next thing we can do is merge two sorted words. Let's say they each have k items, and k is at most log n log log n. And I want to merge them into one sorted word with 2k elements. So I have two of these things, and I'll merge them in sorted order. Okay, when I did this packing, nothing's sorted, but don't worry about that at the moment. Just if I had two of these words, and suppose they were already sorted, then I want to merge them and make them still sorted. Okay, I want x1 to be less than x2, and so on. How much time? It'd be cool if you could do this in constant time on a transdichotomous RAM. You could do anything on a constant number of words in constant time. We're not going to achieve constant time, but we don't need to. We're going to do order log k time. This is the hardest step of pack sorting, and I'm not going to tell you how to do it until later. I will tell you, don't worry, but this is going to require bitonic sorting. So I have to delay it a little bit. Suppose you had that for now. Let me tell you how the rest is easy. So many black boxes, but they're all filled in this lecture. Okay. Next thing you might ask is, well, how do I get a sorted word? I see how to get a single word that has log n, log n items, but how would I sort those items? Use merge sort. Here's a merger. You have a way to merge two sorted lists, so use merge sort. That will give you a way to sort the whole thing. So I'm going to merge sort k equals log n, log n items. Into one sorted word. So I start out with a word that's unsorted. I do merge sort, and I sort them. Okay, so this is not the whole sorting problem, but it's the one word sorting problem. So how long does this take? Well, it's the usual merge sort recurrence, but then it's plus how long it takes me to split the word. Well, splitting a word is easy. You just mask out the low end or the high end, and then maybe shift over. So in constant time, I can get the left half and the right half of the array, which is the word. Then the hard part is merging them, and merging them is 1, and that takes log k. So this is step 1. That's our merger. And so what does this solve to? Well, probably easiest to draw the recursion tree. So at the root, we pay log k. Then we have 2 times log, I guess, k over 2. Log k over 2. Okay, so at this level, we're paying log k. At this level, we're paying 2 log k minus 1, I guess. Okay, I'm just going to call this maybe, well, yeah, I do need to do that. At the bottom, I mean, everything's constant size, so you pay constant. How many leaves are there at the bottom level? K of them. Okay, so at the root, we're paying log k. At the leaves, we're paying k. This is roughly geometric. There's this minus 1, but it's geometric enough that when you add up all these levels, it's dominated by k. And so this ends up being order k time. Okay, the minus 1 here turns out not to matter much. Cool. So this is linear time sorting on log n, log n items. Everything that fits in a word. Cool. But we're not done yet. We need another level. The rest is pretty easy. It's just scaling up. Okay, let's see. At this point, we're going to assume that all of our words are completely full. So this merging and stuff was in order to fill up words and to make those words sorted. But once we've done that for each cluster of log n, log n items, now we can assume each word is sorted and completely full. It has exactly k elements in it. So each of these r-sorted words has k elements. Okay, so now the issue is things don't fit in a word. And so now suppose they fit in r-sorted words. So suppose we've already made a sorted list of of r times k items, which fit in r words, each with k items in it. Then I want to take two of these lists and merge them together and get one sorted list of sorted words. So it's two rk items that are distributed into two r words, each of size k. How do I do that merge? In linear time. And I only need to do it in r log k time. Only. Yeah, question?
You're assuming k is the number of elements per word now.
K is this from now on, and they're exactly k elements per word. Which is, I mean, we've already filled up the words, so at this point we can assume that.
Okay, but it's exactly equal, not less than or equal.
Right.
As in one or what's less.
Yeah, over here it's less than or equal to. I know it's a little confusing. I use k for a different, call this k prime. Okay, and at this point we filled up to this value of k. And now everything has exactly log n items. Thanks. Okay, let's see. I mean, regular merging algorithm would take r times k time because there are r times k items. But we have this merger over here, which will merge two words in log k time. So that's why it's going to be r log k. What's the picture? Well, let me draw it. We have a list of words, How do we merge? Well, we take the first two words, merge them. When we merge them, and we know how to do this in log k time, by step 1. When we merge them, we get two words. They just are now sorted. Okay? So we've got these two guys sorted, and then there's the rest. I'd like to say output these and repeat, but that wouldn't be quite correct because, well, these guys I can output. Because I've got k items here, k items here. These are the k smallest among all of them. Those must be the overall smallest k items because I compared k with k. These higher k items, I don't know. They could, they might be good or bad. So I have to put this high part back into one of these lists. You have to think a little bit about which list to put it into. It turns out if you look at the max item, say where did this come from, list 1 or list 2, you put it into that list. Let's say this came from list 2. Then you put it back into list 2 and then repeat. Okay, so in log k time here, we have output k items. And so we end up with an r log k running time overall. Okay, so it's like regular merge algorithm, except we use step 1 to merge words. And then there's a little bit of work. But this was like old merging algorithm, right? You take the min and you put the max back in. Okay, except now the max is a whole word. Okay, that's how we merge. Now why do we do a merger? Because the next thing we do is merge sort. And this is the overall algorithm. It's one merge sort. We're going to use this as the merger, and we're going to use this as the base case. So it's actually two recursive levels of merge sort. Merge sort is recursive within step 4 for a while until we get down to the level of a single word. Then we use this thing to deal with things in a single word. Okay? So we end up with t of n is 2 times t of n over 2 plus n over k log k. And a base case of t of k is order k. Okay. Why is it all this? Okay, this thing is r. Okay. So we have r log k to do a merge. R here is n over k. Why is it n over k? Because n is the total number of items. We had r times k items, so n equals rk. So r equals n over k. Okay, that's that. So this is our merge cost. This is the cost of 3. This is the cost of 2. From our, if we have only log n items, so k items, then we can merge in linear time. Or sorry, we can sort in linear time. So we just need to solve this recurrence. Well, how's it going to work? It's going to be kind of like merge sort, but not quite. So, question?
When you say, so you have, in step 2, you're merging 2 lists of sorted words into one sorted list of 2 more sorted words. Does that imply actually taking the elements within the words and reshuffling them across words? Or you may have to do that, right?
Say that again?
So you have two sorted lists of R sorted words.
Yeah, the words are going to change. Which elements are in which words are changing. But that's thanks to step 1. For example, I mean, step 1 can merge any 2 sorted words and make one sorted word. Or actually, yeah, one sorted word. In our case, we're going to get 2 sorted words. That was the picture over here. I merged the 2 guys. I could represent it as one word that's kind of double full, and then I can split that into 2 words. So we, again, need the split operation, but split is just you mask these guys out, and you get the high part. This is all 0. Then you shift it over to the left, and now you've got the high word over as a single word. Yeah. So they are shuffling within those 2 words, or within one word, essentially, via this procedure, which we haven't covered. So everything's going to mix around, but then there's the low items and the high items. And so all the items in here are less than all the items in here. Other questions? Cool. So I need to solve this recurrence. So let's draw another recursion tree. It's an easy way to solve recurrences. Root is n over k log k. Next level down, see n got divided by 2. So it's going to be half n over k log k. Half n over k log k. So the n gets divided by 2. So if I add up everything on this level, I get n over k log k. And in general, as I go down, all levels are going to sum to the same value, n over k log k. So up here, we're going to have a cost of n over k log k times the number of levels. Now, this is where it's a little tricky. This is not log n levels like regular merge sort. We stop at level k. So it's going to be log of n over k. That's the number of levels we get to. Now, at the leaf level, finally, we have things of size order k, and we only pay order k. Great. And then how many leaves are there? There's n over k leaves. OK, so that's an order n cost. This is order k. There's n over k, order n. What's this thing? Well, what's k? K was log n, log n. So this is n divided by log n, log n. This, therefore, is approximately log n. So that log n cancels with this one. This is approximately log n. So that cancels with this one. So this is order n. That's why we chose these values. So this n over k was not actually that significant. We could have called that n. What is important is that this recursion doesn't work when you get down to a single word. You can't do the same strategy. You need to use a different merger for single words. Because here we have to do bit tricks. For this merge strategy, we didn't have to do bit tricks because everything was bigger than a word. Okay, so that's the reason. The reason why we have these 2 levels is not to make the time fast. It's just to make the algorithm work. I mean, to define the algorithm, there's within a word merging and over many words merging. The hard part is this one, within a word merging. So that's our next goal. But if we could do that, we get linear time sorting for packed sorting when you can fit log n, log n things in a word. Any questions about packed sorting? Good. So last thing is, how do we merge two sorted words into one sorted word? And this is where we're going to use bitonic sorting. See, it says right here, bitonic sort for merging sorted words. Here, we know what to do. Much easier in hindsight. So I'm going to take a little diversion and tell you about bitonic sorting briefly. Because it's in CLRS, I don't want to spend too much time on it. But it is something we need, so you need to know how it works. So first thing is the idea of a bitonic sequence. This is going to be a cyclic shift of a unimodal sequence. So a non-decreasing plus a non-increasing sequence. So I want non-decreasing and then non-increasing. So this is a bitonic sequence. I think you know what this means. Or it could be a cyclic shift thereof. So I could, for example, take this part here and shift it over to this side. So then I'd end up with this, this, and this. This is also a bitonic. Or I could shift this whole thing and put it over there. And so I end up with that. That's also bitonic. So it basically has one max, one min, if you're reading it cyclically. One local max, one local min. Except it's non-decreasing, so a little messier, but same thing. OK, let's go be over here. So if you have a bitonic sequence, there's something called a bitonic sorting network, which you can think of as a parallel sorting algorithm to sort such a thing. So it's almost sorted, but not quite. And there's this way of sorting them. So I'm going to draw a picture to make it easier for me. A little harder. It's a little more annoying to write down the general algorithm. So what I want to do, suppose the number of elements is a power of 2. Here's what I'm going to do. First, I compare the first and the midway element, and then the next one with the next one, and then the next one with the next one, the next one with the next one. For each of these comparisons, I put those items in the correct order. So if I do that, 3 versus 6, 3 is less than 6, so 3 stays here, 6 stays there. 5 is bigger than 4, though, so 4 comes over here, 5 goes over here. Next is 7 versus 2, so 2 comes over here, 7 comes over here. 9 versus 0, so 0's over here, 9's over there. Okay, that's an easy set of comparisons to do. The nice thing is you can do all those in parallel. Okay, just to check here, this was a monotone increasing subsequence and then a monotone decreasing. Okay, now we have increasing, then decreasing, and then we have decreasing, then increasing. But if you look at the left half, or the right half, they are still bitonic, and that's an invariant. Bitonic will be preserved here. Also notice all the elements in the left are smaller than all the elements in the right. That's not true for an arbitrary sequence, but it will be true for a bitonic sequence. Essentially, the max is somewhere here, and so it's going to be spanned by some of these intervals, that max. And by spanning those intervals, and in particular comparing that guy with somebody on the right, the max will get over to the right, and then the rest of the increasing and decreasing subsequences will follow. It's a very hand-wavy argument. You can see CLRS for a way to prove that. OK, just take it for granted now. Now we recurse on the two sides. So I compare 3 with 2, 4 with 0. I compare 6 with 7, and 5 with 9. So what do I get? 2 is less than 3. 0 is less than 4. Then I compare 6 or 7, so 6 is less than 7, 5 is less than 9. So now I've got 4 chunks, this one, this one, this one, and this one. I recurse on each of them. So 0 is less than 2, 3 is less than 4, 5 is less than 6, 7 is less than 9. And now I have all my items in sorted order, magically. Okay, but if you believe that invariant, that the smallest n over 2 items get to the left and the larger n over 2 items get to the right, then by induction this will sort them. It's kind of like quicksort in that sense. Okay, the cool thing is I can do all these in parallel, all these in parallel, all these in parallel, so the total time is log k if I'm a parallel sorting algorithm or sorting network. And log k is exactly what I can afford. So the last thing to do is to implement an operation like this or like this. This is kind of the generic picture here in constant time on a word RAM. One other thing, because I don't want to sort a bitonic sequence. That wasn't my goal. My goal was to merge 2 sorted sequences. Okay, so I have 2 sorted sequences. I want to merge them. How do I make that bitonic? I just flip, okay, like that. I take this sequence and I reverse it. If I take a sorted sequence and reverse it, then it looks like this. And so then the result is bitonic. Then I can use bitonic sorting to sort it. So this is the merge problem, and I've just reduced it to bitonic sorting. Cool. Except, how do I reverse a sequence in log k time on a word RAM? Cute trick. If I have a word and it has many items in it, that's our picture, that's our setup here, and I want to reverse it overall, what I'll do is cut it in half, take all these guys, put them over here, take all these guys, put them over here. So I've got the right side, sorry, it's only 4 cells over here. I've got the left side over here. Then I recursively recursively reverse this sequence and recursively reverse this sequence. And then I have the reverse sequence. Right? This is a standard, or one way to reverse items is to do the big part and then recursively reverse. Then I will get, this is like, AB reverse is equal to B reverse A reverse. Just a fun fact. So we're implementing that. Now, how do I do this? Well, this is the thing I've been talking about over here. You want to take the high part, you just mask that part out, shift it to the right. You want to take the low part, just mask that part out. And so I can take each of these parts individually, shift this one to the left, shift this one to the right, or them together, and I've reversed. So this takes constant time. This is recursion, but the total number of steps will be order log k, which is exactly what I can afford. Okay, so that's how I do the reverse part. So if I want to merge, now I have a bitonic sequence. Last thing to do is how do I do this bitonic comparison in constant time? So that's the next page. Here's a quick sketch. I'm going to try to draw the generic picture. So the generic picture is I have this thing which I call A and this thing which I call B. And we basically want to compare corresponding items in A and B. Though in fact, there's another A over here and another B over here. In general, there are many A's, many B's, but they appear in this nice periodic pattern. And so I'm just going to look at one A-B pair, but it's going to simultaneously work for all of them with the same operations. So that's the ... here. There's another A, and then another B, and another A, and another B. So what do? First thing I do is make 1 AA, 1 AA, 1 AA. In other words, I add in these 1 bits. Remember, we had zeros there hanging out. That's when we're going to use them. So I set them all to 1s in the A list. I take the B list, I just shift it over and leave them as zeros. Okay, time for bit tricks. All right, then I take this number, I subtract it from this number. What do I get? I get zeros or ones for whether this bit got borrowed, which tells me whether little a is bigger than little b. Then I get some junk, and then I get 0, 1, junk, so on, 0, 1, junk. Sure. So 0 corresponds to a being smaller than b, and 1 corresponds to the reverse. Okay, whatever. Then I do my usual masking, just the 0, 1 bits, then there's some zeros. Okay, here's a new trick which we haven't seen yet. I'm going to shift this to the right by 2, or in general by the size of those items. So now I have 0, 1 here, 0, 1 here, and 0, 1 here. Each of these bits might be different. So I take this, shift it to the right. Now I subtract. What this gives me, so I'm taking 1, 0, 0, 0, minus 1. What I get is 0, 1, 1, 1. Okay, in this case, there's just 2 bits. Except it's not 1, 1. It's either 0, get it right, either 0, 0 or 1, 1. And then we have here 0, and then 0, 0 or 1, 1. Okay, and so on. So now these are masks. The zeros correspond to when the a's were smaller. The ones correspond to when the b's are smaller. So if I take this ANDed with this, I get the large b's. If I take this ANDed with this, I get the small a's, or some of those combinations. Okay. The point is, I think here I get the small a's. And then if I take this thing and negate it, and then mask it with this, I get the small b's. And then I take this thing, I ran out of room. So we've got small a's, small b's. I take this thing, I shift it over, so I have small b's here. And then I OR these together, I get all the smalls. Okay, these are designed to never conflict, because I took the inversion here. So I get the smaller of the a's, smaller of the b's. So now I put the smaller things in the right order. I do this exactly the same procedure negated, and I get the larges. Okay, then I OR these together, and I get sorted. Well, not sorted. I get whatever bitonic sort would have done. Right? It's doing these pairwise comparisons by doing this shift, and it's putting things in the right order. Taking the small ones always end up on the left, the large ones always end up on the right. That's the definition of the operation we want to do, or is bitonic operated. And because we were just doing shifts and subtractions and all these things, it works even though there's not just one A-B pair, but there's a whole bunch of A-B pairs. They will all be shifted and computed and sorted together. So a little hard to visualize, but this will do one bitonic operation and a constant number of word RAM operations. And so you pop all these stacks. This gives us a merger. That gives us pack sorting. And with pack sorting, we get signature sorting. Easy, right? All right, that's probably one of the most complicated algorithms we'll see in this class. But from that, you get a priority queue that runs in constant time provided W is a little bigger than log squared n. Boom.